Hello again. So today we're going to be talking about secondary flight controls, and there are goals for the day. So we're going to watch this video of a short takeoff and landing, and I want you to be thinking about these questions that you see posted here. Alright, so yesterday we talked about 3 primary flight controls here. So hopefully you guys can remember what they are. Ailerons, they control the roll, they're located on the wings. Elevator controls the pitch, it's located on the horizontal stabilizer. And the rudder controls the yaw, which is located on the vertical stabilizer. Alright, so here are some secondary flight controls. This is going to improve the performance while relieving excessive aerodynamic and control forces. So we're going to cover each one of these here coming up soon. The wing flaps, leading edge devices, trim system, and the spoilers. So secondary flight controls aren't on all airplanes, but you need to know what they are and how to use them, especially if you're going to be flying bigger, more complex airplanes. So flaps are the most common secondary flight control system. They're found on almost every airplane. A flap is a movable surface attached to the trailing edge of a wing. Sometimes flaps are located on the leading edge. This type of flap will be discussed as a leading edge device. A flap is considered a high lift device. Deploying flaps increases the wing's camber, which increases lift. So as you learned in the last unit, drag is a byproduct of lift. So therefore, deploying your flaps also increases drag. The pilot can extend flaps to increase lift when needed, so during takeoff or landing, or retract them into the wing when they're not needed, so when you're cruising. So flaps deployed at different angles are deployed at different angles during different phases of flight. So we can look at these illustrations here. So A, that's during takeoff and initial climb. So flaps may be extended typically 10 to 15 degrees to generate more lift and increase the climb gradient. So B is cruise, so you can see that it's more streamlined. And then C is your final approach. Flaps are extended to change the wing's camber, which generates both lift and drag, enabling a descent at a steeper angle and lower airspeed. In lesser degrees of flap deployment, typically 0 to 25, lift increases significantly more than drag. But once you get greater than that, drag increases more significantly. So because flaps increase lift and drag, they're often deployed at some degree during takeoff and landing. The main benefits for flaps for takeoff and landing include a reduced stall speed. So extending flaps reduces an aircraft's stall speed because the wing creates more lift with the flaps down. This means an aircraft can fly at slower speed on landing without the risk of stalling, and we saw that in that video we just watched. So shorter runways, airplanes can lift off quicker at lower speeds. They can increase drag, so extending flaps increases drag. What else we got? So using flaps on landing gives pilots 2 distinct advantages. First, the airplane has a slower stall speed, which means it can land slower. Second, the airplane produces more drag, which allows it to fly a steeper descent angle to the runway. So, thinking back to the video we watched, the flaps were key to allowing the pilot to land both slow and steep. Alright, so there's different types of flaps here. So the plane flap, this is the most mechanically simple. It is a hinged portion of the wing's trailing edge. It increases the wing's camber, which increases drag, as well as the coefficient of lift. It does not increase the wing surface area. So then you can see the split flap. It is a hinge portion that's deflected from underneath the wing's trailing edge. So it produces slightly more lift than plain flaps, as well as more drag due to the turbulent air pattern it produces. Like a plain flap, it increases the wing's camber, but not its surface area. So although they are cheaper to make, both plain and split flaps produce high drag with minimal additional lift. So the slotted flap is found on both small and large, and there are many different types of slotted flaps. Some large aircrafts have multiple slots in the flaps. So when deployed, there's a slot between the flap well in the wing and the leading edge of the flap. This slot forms a duct of air between these surfaces. This gap forces high pressure air from below the wing over the upper surface of the flap, which helps keep airflow continuous. Because of the delay in airflow separation, it also increases the maximum coefficient of lift more than plain and split flaps. Like plain and split flaps, it only changes the wing's camber and not the surface area. So the last one there, the Fowler flap, which is a type of slotted flap, instead of it being hinged, it moves backward on a track and extends beyond the trailing edge of the wing, which increases the surface area and the camber. So among flap types, it has the highest lift to drag ratio and its lesser degrees of extension, giving it the greatest aerodynamic advantage. And this one is also the most expensive to produce. So now we're going to talk about leading edge devices. So like flaps, these devices help the aircraft fly at lower speeds. Unlike most flaps, they are attached to the leading edge of the wing rather than the trailing edge. Leading edge devices change the wing's camber and/or surface area. The exception is to the fixed wing slots, which don't move and therefore don't change the camber or surface area of the wing. So remember that whenever more lift is generated, more drag accompanies it. So the leading edge devices will always produce more lift and drag. Leading edge devices have a gap or slot that directs air over the top of the airfoil to delay airflow separation. By keeping the airflow continuous against the wing's upper surface at high angles of attack, the leading edge device produces more lift, lowers stall speed, and changes the critical angle of attack. So without a slot, the airflow over the upper surface would separate sooner. Alright, so instead of just reading through all this again, I'm just going to let you guys read it so you can pause it and read through all this. Alright, so we have played around trim a little bit. Some of us are a little better at adjusting the trim than others. So we're just adjusting the control surfaces to maintain the desired flight attitude. So without the trim, before we started practicing with trim, we were constantly making adjustments trying to keep our desired flight path. So trim systems, when they're used properly, help alleviate this pressure. So trim systems can reduce pilot workload and fatigue by alleviating pressure on the primary controls. And this also helps maintain your desired airspeed and flight attitude. So we need to remember that we must retrim the airplane to hold the desired flight attitude after any change in airspeed, angle of attack, or configuration like deploying flaps. So here we can see the trim tabs. So the trim tab is a control surface attached to the elevator, aileron, or rudder. This allows the pilot to make subtle adjustments to balance the forces on the elevator, aileron, or rudder. So we can adjust these by adjusting the trim wheel or trim switch. So look at the following example here. So when a pilot increases airspeed, lift also increases. This tends to pitch the nose of the airplane upward. So in order to return the desired flight attitude, the pilot needs to exert forward pressure on the yoke to bring the nose back down. If the pilot takes no further action, he'll need to maintain the forward pressure to keep the airplane in the desired attitude. But if you adjust the elevator trim tab upward, you can relieve the pressure, allowing the airplane to maintain its desired attitude without constant pilot input. Alright, so spoilers, or we call them speed brakes, are perhaps the most counterintuitive of secondary flight control systems. They do in fact spoil good aerodynamics of the airfoil and creates a lot of drag and reduces lift. These qualities are useful in certain situations, so when do you guys think that might be helpful? Yeah, you're right, probably you said slow down. Be a good example. Alright, so here we're just going to see the spoiler functions in these videos. Alright, so that's the end of our lecture over secondary flight controls, and again below this will be the assignment that I need you to turn in. Hope you guys have a great day.